So now we want to apply our backpropagation and want to test the full backpropagation because we have the backward part, we have everything implemented, and if there are no typos, the RNN should be able to learn, and we just want to test this. So we so before we set up our actual optimizer, we just want to test run it in our code. So we just import the RNN, then just call the RNN itself, and want to run it for a few epochs. And also we want to start with a relatively small learning rate, because what I said at the beginning is that the RNN, or the classical RNN, struggles with the exploding and vanishing gradient. So we want to be a bit careful with that. And that's why we just want to have a small learning rate, because also the weights are adding up the information from all the previous time steps. So I just want to be careful with that and just set up or start with a very small learning rate. And then we just call the forward part, which generates y hat, calculate the loss function. We also want to print the loss function. Then want to call the backward part, because the backward part uses dy to calculate the change of the derivatives. And also want to just remind you on the mathematical part earlier. So we have the dy, and this is this part here. And the yellow part, so the yellow part of the derivatives, that's already done internally. So that's what we just have done and tested in the previous chapter. So therefore, the only thing that we need to do is the part which is highlighted in red here. And it's taking those weights and then multiply them with the learning rate. So this is this part here. So our E is our epsilon. And then it should update those weights accordingly in terms of minimizing the loss function. So this part is this part here. And of course, we want to plot this and see whether it works. So that's the task now, that we want to run the forward and the backward part of our code and just take a look at the loss function and also at the result. So therefore, let's go back to our code. And also here, I would recommend to open or create a new folder and open a new chapter. Let's call it full backpropagation. And we also want to navigate to this folder and also save everything. Oops, I of course want to save it in this folder. So, and also save this in a folder. All right, so we want to compile our RNN. And now we want to test run our RNN. So we just start with initializing all those values that we need. So we have in our data set here, then we have the number of neurons. That's already, that's also already correct. We also need this part. And so we just call the neural network again. So now we just start with a relatively small number of epochs. So it's just for the principle. So let's say, yeah, just 20. So just really showing how it works in principle. Let's say 20 epochs. Then E, the learning rate, is also a value that's relatively small. And now we want to start with the actual calculation. So now we just open a loop. Where we just call the forward part and the backward part in order to optimize our loss function. So we start with RNN forward, then that generates our prediction y hat. Which we can access via RNN dot y hat. And based on y hat, we can calculate the discrepancy between the prediction and the actual training data. And based on that, we can calculate the loss function. And we also want to print the loss function. So we just say print float L, so that just, so we use float just that it looks nicer. We don't need this part anymore. And we also want to print y hat and y in the loop, so that we see how our prediction makes progress by minimizing a loss function. So we want to see this, but we also want to see the plot. So we have the forward part, which generates the y hat, the vector for y hat, so the prediction. We can therefore calculate a loss function and calculate L, so dy and L. And then once we have dy, we can use it for the backpropagation part. So the d values are now dy. And that generates the values for the d weights. So we just calculate the weights then, or update the weights by using our learning rate. And we do this for the d weights. And then we just copy and paste it. Do it for all the other weights. So for the biases and all the other weights. And also here, again, it's not necessary to keep it all in line, but I just want to do that. This looks better. Okay, so we have the entire code now that we want to test. So I want to expand this, that you can see it. And we should now be able to run the code. So we call the RNN, number of epochs, learning rate. Then for a certain number of epochs, we run the forward part, the backward part. And I also want to show the plots, and let me also add a title, because I also want to give a title according to the number of epochs. So let's just write it epoch. And yeah, just plus, and just keep it simple, plus string L, sorry, N, so the number of epochs. All right. So yeah, let's run it. So let me just delete this part, and then let's run it, and let's see what it does. So we get an error message. And let's just go and fix the error message. So we actually have one initial value, and we get an error message. So now let's go and fix the error message. Let's see dy, so dwy, it's, yeah. So I think that's the problem. Let me just test this. Oops, because we forgot the transposed here. And then let me just test run it again. So there must be a transposed here, because remember, y is a row vector. And now let's see what it does. Still doesn't do what we want, but at least the shapes seems to work. So then again, let me just try to fix it. Okay, so that was actually an interesting error that happened. So let me just show why it didn't work. So I forgot the epsilon here, and if I run it, you see it doesn't work at all. So let me just stop it. And I forgot the epsilon here, and let's run it again. And that's actually interesting. You see the impact of the bias of the learnable. So I'm still not 100% happy. Let me just interrupt it again. So there would be nice if there's a playing. So this was the here was the reason of the debias that it didn't work. And also we forgot, well, I forgot the transposed here. And let me also just save it in the previous chapter so that it's all complete and just save it here. Yes, of course we want to override it. Okay, but now let's take a look. So it kind of does something. And let's rerun it now and test it. And one more time. So let me just remove that. So what we see is that the loss actually goes down. So that looks very promising. Therefore, let's test it with a larger learning rate. Maybe it goes faster. Let me also just delete this part. So that's the problem with the exploding gradient. So once you just start with a value that's a bit too far off, then it just ends up with large numbers and then doesn't come back to that. And actually you see it's just the training part is pretty challenging. So let's start with again with a smaller one, and let's also increase the number of epochs, and let's see how far we get so that we see at least some improvement in some that just fits and it's not looking so bad. Of course, there's some noise, so it will not be better than the noise actually, but the numbers are going down. And you also see how it tries to understand the structure of the data. And of course, we haven't optimized the learning or also how the network is learning yet, but still it's getting better. And you also see how it's moving now. So let me actually just run this. So I mean, it's a video, so if that bores you, you can of course skip it. But did you just see how it works and how kind of optimizes now the plot? So maybe I should just click on the pause it and show you then later. Okay. So it's done now. So the average error is like 9%, even a bit less. And let's also see on the plots how it actually improved it. So that was the training data. That's the initial plot. So before the backpropagation process has been started and before the weights have been adjusted. And that's the first epoch already. And you see how it's improving now gradually and constantly. And it's still not being optimized. So I guess the code is on a good way. And after 200 epochs, you have a considerably acceptable result, so to say. So the code works, and we have removed these little typos. So here was a typo. And again, it was also interesting what happens if you just cut out the bias. And so after a few epochs, you should see some progress in improving the fit. You might see some artifacts like this at the beginning, which can happen because we just choose the numbers randomly. But if you run like 200 epochs, like in my case here, you definitely should see an improvement. And also the loss function goes down. So that's a good sign. It might also go up in the first moment. But what you have seen is that it's very sensitive to the learning rates. We definitely should run now an optimizer on that where we can adjust the learning rate. So for example, where we can apply a learning rate decay, and also maybe adding some momentum is important. And this is what we are going to do next. So our code works, our RNN is able to learn. So we are ready now for creating an optimizer. And this would be the stochastic gradient descent optimizer. And that's what we're going to do in the next chapter.